Hey guys, so we have 5 MCQ questions over some work and energy, and these are going to be like real style MCQ questions. Not just going to be giving answers, but we're going to break down how to solve each one. All right, so let's start with the first one. So some mass M is attached to a horizontal massless spring with spring constant K, is set into simple harmonic motion. Its maximum displacement from its equilibrium position is A. What is the mass's speed as it passes through its equilibrium position? Okay, so this is a simple harmonic motion question, and the key to solving it is going to be energy conservation in simple harmonic motion. Now, in simple harmonic motion, at maximum displacement, so the amplitude, so we'll see that right here, the mass is at rest, so all the energy is stored as spring potential energy. I like denoting that as just potential energy spring, with just a little s. And at equilibrium, the spring isn't stretched nor is it compressed, so all the potential energy is zero, and all the energy at that point is going to be kinetic. So all the energy here is going to be 100% kinetic. And then at the amplitude, it's going to be 100% potential spring energy. So let's first write out our two energy forms. So we have potential energy at the amplitude, which is going to be 1/2 Ka squared. And then we're going to have kinetic energy at its equilibrium, which is going to be 1/2 mv squared. And since total energy is conserved as it goes from the amplitude in this first point through its equilibrium at this point, we know that all the potential energy is going to be conserved to kinetic energy. So we'll know that 1/2 Ka squared is equal to 1/2 mv squared. And we're trying to find the mass's speed, which means all we have to do here is just solve for velocity. So that cancels out. We're going to divide by mass. We'll get v squared equals Ka squared divided by mass, square root on both sides, and we get v equals, the a comes out of the square root of K over m, which leaves us with option B. All right, question 2. A force F at an angle above the horizontal is used to pull a heavy suitcase of weight mg a distance along a level floor at constant velocity. The coefficient of friction between the floor and the suitcase is mu. The work done by the frictional force is... So I already went ahead and made some things that'll make this easier for us. I underlined constant velocity over here, and I made a little diagram. Now, why did I underline constant velocity? Well, we know, according to Newton's first law, that if the object isn't speeding up or slowing down, it's moving at a constant velocity, as we know, all the forces are balanced. There's no net force, no acceleration. And another thing I want you guys to notice is that the question isn't asking about the pulling force, it's asking for work done by the frictional force, so the force fighting against the motion. And which direction is friction acting? Opposite to the direction of motion. Now, I drew this little diagram of what's happening here. The heavy suitcase isn't moving up, right? It's moving some distance d along this floor. And work, the only force that matters in work is the force that is acting in the direction of the motion, right? So the only force that we're worried about here is this one, which would be, if that's the hypotenuse, that would be F cosine theta, right? And friction acts opposite of motion. So friction, I'll just call that force friction, is acting the opposite way. And since we know that the forces had to balance out in order for there to be a constant velocity, we know that F cosine theta had to have been equal to the force of friction. So now when we're trying to find the work done by friction, we can just substitute in F cosine theta in. So that's going to be F d cosine theta. Just a reminder that the formula for work is force times distance. And in this case, since our force has a component, then we're going to add that component for our work. And don't forget the negative there, because it's acting opposite of our motion. It's a negative work, which would give us option A. All right, question 3. A 2 kilogram ball is attached to a 0.80 meter string and whirled in a horizontal circle at a constant speed of 6 meters per second. The work done on the ball during each revolution is... All right, let's be real. This one might mess people up. So the ball is clearly moving, and there's a force from the string pulling it in, which is tension. So you might be thinking, of course there's work being done. The thing's like flying around in a circle, right? But here's the twist. This is actually, I'm giving you the answer here. It's a zero work situation. And I drew a little diagram if my diagram didn't already give it away. So during circular motion, the ball is moving tangent to the force, tension. So let's say now if it was over here, tension's still acting that way, and the ball's displacement is still going this way. So there's a 90-degree angle here, 90-degree angle here. If we think about work equals F d cosine theta, a 90-degree angles means we have cosine of 90, and cosine of 90 is equal to 0, which would make everything equal to 0 here, and work would be equal to 0. All right, question 4. A pendulum bob of mass m on a cord of length L is pulled sideways until the cord makes an angle with the vertical as shown in the figure to the right. The change in potential energy of the bob during the displacement is... All right, so let's zoom in on this over here. So when the pendulum is hanging straight down, that's its lowest point. So we'll call that point 0 potential energy. And imagine we start pulling this over there. We just start pulling the bob over there to the angle theta. The string length is still L, but the mass rises vertically by some amount. That height difference, we'll call it delta H, is where the change in potential energy actually comes from, because we know potential energy is mgh, right? So the hypotenuse is the full string length L. And the vertical side, so from the height from pivot to new position over here, is L cosine theta, right? So the change in height, as we know, at this 0 potential energy point, it's just L, right? So our change in height is going to be L minus L cosine theta, right? So if that's the change in height, that means our change in potential energy would have to be mg times this change in height, or just L minus L cosine theta. Now let's look at our answer choices. I see that none of our answer choices are like that, but I do see if I take out an L from the parentheses, I'll get mg L 1 minus cosine theta, which matches A. All right, question 5. A softball player catches a ball of mass m, which is moving towards her with horizontal speed v. While bringing the ball to rest, her hand moved back a distance d. Assuming constant deceleration, the horizontal force exerted on the ball by the hand is... All right, so here's what's happening. So a ball is flying towards the player. She catches it, but instead of stopping it instantly, she lets her hand move back a bit, like kind of like she's absorbing the impact. So this is a work energy problem. And the ball has some kinetic energy while it's moving. So kinetic energy equals 1/2 mv squared. And then the glove applies a force to bring that energy down to 0 over some distance d. So the work done by the glove is work equals force times distance, right? But here's the subtle part. The force is opposite the direction of motion, like I think question 2 earlier. So the ball's going right, and the force is pushing left. So technically, negative FD is equal to our change in kinetic energy, right? And our change in kinetic energy is just going to be 1/2 mv final squared minus 1/2 mv initial squared. The final velocity is 0, right? Because she stops the ball. So that's just going to be 0. So now what do we have? We have negative FD equals 1/2 mv initial squared. Note that the horizontal speed over here is the same as v initial. I just didn't mark. I just put the initial. So now all we have to do is just solve for the force. And when we do solve for force, hold on. This is actually a negative 1/2 mv initial squared. When we do solve for force, we'll get force equals mv squared over 2d, which is A. If you were wondering why I put in that negative for that negative 1/2 mv initial squared, it's because change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. I just forgot to include that negative. So yeah. All right. Well, that's all 5 of the questions. So to recap, it was B, A, D, A, A. And I hope you guys understood everything. See you guys.